All right, this video is starting on page 551. This topic it might sound a little bit unusual, but it is called the Pythagorean theorem. Let's say it one more time: Pythagorean theorem. This video is going to go until page 554, so not that many pages, but we are going to transition. So we are going to after that we're going to go through our guided notes. So you should have an additional paper outside of your book. So predominantly we're just going through this warm up and then focusing on activity one, then switching over. Okay, so learning goals here is we're going to make improve. We're working with Pythagorean theorem and to find unknown side lengths. So we'll talk about what it is, what's it used for, and where would you see this. So let's start on our review though. So we're solving for a variable. Normally we don't solve equations that are kind of revolved around these various symbols here. So we have squares. But I want you to think about in terms of this. So number one, we need to think about what number goes in for x to make this equation true. And if you look on the left and the right, you might be able to notice some things. So we have 8 squared is equal to x squared. So we're thinking about what number needs to go for where we highlighted for to determine to make that left side and the right side equal. So here, in order to make this equal, right, we can see that this has to be 8. So our answer could be 8 equal to x. Right, so if I put an 8 right here, right, the left side will be equal to the right side. All right. Now, as we're going through this, look at example 2. We're thinking of what number, if you square it, if you multiply by itself, it's equal to 36. In that case, that x value has to be 6 because 6 times 6, if I put the 6 right here, 6 times 6, 6 squared is 36. All right. And similar for number 3, right? What number do we have to square to equal 25? Right, so this x would have to be 5 because 5 times 5, right, is 25. So similar to number 2. But number 4 is somewhat different. X squared is equal to 90. 90 is not a perfect square, but the answer for this, the x would have to be the square root of 90. So we'll talk more about this in our guided notes. But whatever square root of 90, if you plug this into your calculator, I mean, we could plug it in right now. Let's put 90 in the square root of that. So it's non-terminating decimal, or irrational decimal. It's 9 point. We'll round this to 5, so 9.5 roughly. So if you put 9.5 times 9.5, it's going to be approximately equal to 90. All right, let's go and move on to the next page here. So this is searching for the right pattern. We have various triangles. We're not going to work with the last two. Well, that's interesting. There's somewhat of a glitch on here. So there's 6 triangles. We're just going to work with the first 2. But let's actually start with our worked example here. So this first one is actually working with this first triangle. So we have a right triangle. And so the right triangle is a triangle with a right angle. And that right angle is 90 degrees. And you can see this square here, that represents the 90 degrees. Okay, so a square drawn in the corner formed by the angle indicates the right angle. So what it's asking us here, it says if you square the length of each side, so square each side of a triangle, you get these values. So looking here, we have a 3, a 4, and a 5. So we squared 3, that equaled 9. We squared 4 to equal 16. We squared 5 to equal 25. And then also for triangle B, we have 6, 8, and 10. So 6 is 36, 8 is 64, and 10 squared is 100. So we're trying to find some type of pattern here. But let's go through the other ones. So triangle C, so this one, 5 squared is 25. Let's go to the next biggest or bigger one, 12 squared, right? 12 times 12 is 144. And then we'll do the biggest one here, which is 13 squared, which is 169. Okay. And we'll end it on triangle D. So 8, 8, 15, 17. 8 squared is 64. 15 squared, I don't think we have that on our list, but we can multiply 15 times 15, right? That would be 225. And then 17 squared, 17 times 17 is 289. So there's some type of pattern that we're looking between these two triangles and this bigger, or these first two triangles that are in the worked example. So number 1 says repeat the process. We did. Do you see a pattern in the squares of the side lengths of a right triangle? And if so, describe it. So I'd recommend pause the video here, see if you can see anything that we've done so far, any patterns that you notice, and then continue the video. But we're gonna debrief this soon. Okay. So I'm gonna circle the numbers after we squared it. So 9, 16, and 25. I'll circle these perfect squares. I'll circle these perfect squares like this. I'm going to circle the first two and then the last one separately. The first two and then the last one separately. And then what do you notice? If you didn't notice the pattern prior to it. Okay. So it turns out that if you add these two squares, it's equal to the last one. So if you add 25 plus 144, it's equal to 169. Let's work with this one. If you add these two, 9 plus 16, right, it's equal to 25. 36 plus 64 equal to 100. And even the last one, 64 plus 225 is equal to 289. So this is a pattern that we see in nature, in construction, architecture. This is just a property that's true. Let's describe this. So it is the sum, right? Sum means to add or total. The sum of the squares we'll say of the shorter sides equals, right, the square of the longest side. Square of the longest side. I'm just going to say the longest square side. Okay. So with that comes new vocabulary, but also formulas to introduce. So we're going to look at the next 2 pages. So activity 1. This is introducing the Pythagorean theorem. That's right. It's going to take you some time to pronounce. Theorem just means a rule, and Pythagorean is named after old famous mathematician named Pythagoras. We can go into the history later, but for right now, let's focus on the rule here. So when you have a right triangle, we've labeled it A, B, and C. And notice the difference in color here. It says the side opposite the right angle in a right triangle is the hypotenuse. So the right angle is here. The side opposite, you always draw an arrow. That side length is called another vocabulary term, called the hypotenuse. Hypotenuse. So that's that side. That's always the longer side. And then here, the other 2 sides are the legs of a right triangle. We're noting this with A and B. These are interchangeable, A and B, just like how you all have 2 legs, right? This triangle has 2 legs as well, right? So 2 legs and a hypotenuse. So A, we actually already answered which side length must be the longest. The longest is the one that's always the biggest, hypotenuse. So that's because the angle is opening up wider. And it's always going to be the one that's opposite of the right angle. Okay, and then from here, B, describe the relation between the side lengths of any triangle. Right, we already said that the sum of the lengths of the two shorter. So the sum of the lengths of the two shorter sides, we'll say lengths of shorter sides, lengths of the two shorter sides is, so not talking about the squares, but if you were to add them, is greater than the longest. So greater than the longest side, the hypotenuse. So meaning, if we look at our first one, 3 and 4, that's equal to 7. That's bigger than 5. Right? 6 plus 8, that's 14. That's bigger than 10. And then we'll do one more. 8 plus 15, that's 23. And that is bigger than 17. So just if you add them, it's bigger. Okay, the rule here. So the Pythagorean theorem is not just a formula. When we say theorem, it's typically like a sentence. It's what we call a conditional statement. It's if this thing happens, then this other thing happens. And this only works with, the special relationship only happens with right triangles. So no other type of triangle can you apply this to. So it says here the sum of the squares, so sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse. We're also going to look at this like visual later. So the way that we'd read this, the two legs here are A and B, and the hypotenuse is C. So this formula here that we would typically use is A squared plus B squared is equal to C squared. This is something that you'll definitely get a lot of practice, and you'll hear this quite a bit. I mean, you can ask any of any algebra students. If you ask them what the Pythagorean theorem is, like 99% of the time, I can guarantee that they'll probably say that correct formula. All right, but let's look at the worked example on this last page, and then we're going to switch this to the guided notes. So it says, looking at this triangle, we have these side lengths of 3, 4, and 5. So if you square those numbers, 3 and 4, 3 squared is 9, 4 squared is 16, and if you add them, 9 plus 16 is 25. And then now looking at the hypotenuse, which is 5, if you square that, it's also equal to 25. So with this, the last sentence here says, therefore, 3 squared plus 4 squared is equal to 5 squared, which verifies the Pythagorean theorem. We're just going to verify these other things. We're actually just going to look at number 2a. We'll skip b. Let's plug this into the Pythagorean theorem. A squared plus b squared is equal to c squared. We'll say that this is a, this is b, and the longest side or the biggest number is always going to be c, hypotenuse. So a is going to be 8, b is going to be 15, and c is going to be 17. All right, and let's simplify this. Let's square. 8 squared is 64, 15 squared is 225, and 17 squared is 289. If you add these two numbers here, adding the ones place is 9, the tens place, 6 plus 2 or 60 plus 20 is 80, or 8, and a 2. You may notice here, this is a true statement. So we would just say if a triangle had these 3 side lengths, it's a right triangle. Okay. All right. So we're going to stop it there. We're going to switch to our guided notes. So you're welcome to close your book and open up to that. So let's look at the guided notes that says Pythagorean theorem on top. Okay. So looking at this, the Pythagorean theorem, the question of what is it? It's a statement. So if a triangle is, and then filling in the blank, this is a right triangle where it has one right angle, then we would say a squared plus b squared is equal to c squared. Okay, underneath this, we have the converse. A converse just means that the conditional statement is switched. So it looks like this. Pretty much what we have underlined is changed in the statement. So how this would read is if a squared plus b squared is equal to c squared, just like we did in our last example. If this thing is true, then we can say a triangle is a right triangle. That's what we were proving earlier, that we got a true statement. Oops. Right, that told us that those side lengths make a right triangle, or one of the angles is a right angle. Okay. So the side lengths, let's just properly describe these. So we have A and B as our legs. These are typically the shorter. I want to say typically, these are the shorter sides. And these, when we plug this into the formula, it's fine if you switch A and B. And then for the hypotenuse, right, it is always opposite the right angle. And here, right, whenever we look at a right triangle, it is always the longest side, or if you have measurements, it's always the longest measurement. Okay, we're going to prove the Pythagorean theorem. So why is this thing true? So using this diagram off to the left, let's plug this in. So this right here, the left side, the height of this has a height of 3. The width of this has a height of 5 or 4. And the hypotenuse, this has, if you count the squares, it has 5. So if we plug those in, I'm going to put them in that order. 3 squared plus 4 squared is equal to 5 squared. Oops. Right, 3 squared is 9. And as you can see in the diagram, right, there are 9 squares right next to that side length. 4 squared is 16. And again, if you look right here, if you count, there's 16 squares. So we're saying, and also 5 squared is 25. So there's 25 squares here. And if you count these two, the total of these two side length squares, right, it's equal to 25, which is the same thing as a hypotenuse. So that means that this is a right triangle. Okay, so we have a couple examples. Example 1, it says determining right triangles. We're going to determine this angle right here. I'm going to put a question mark instead of a square. Is that a right angle? Right? It might look like 90 degrees, but it's sometimes difficult to prove it. Right? We don't know if it's like 91 degrees or 89.2 degrees. It could always be off. But it turns out, right, if it has this property, it's exactly 90 degrees. So we have to figure out in the formula what's A, B, and C. We know that this, the opposite of that supposed right angle, that's going to be C. So we're going to put 8 is C. For 3 and 5, we did say earlier how we can interchange it. So we're going to say A is 3, B is 5. But it could be B is 3 and A is 5. But C has to be 8. So let's plug this into this formula. 3 squared plus 5 squared is equal to 8 squared. If we simplify this, 3 squared is 5. Or sorry, 3 squared is 9. 5 squared is 25. And 8 squared is 64. If you add the left side, that is 34. We have that equal to 64. Notice how that is not a true statement. We're going to put a slash there, so it's not equal to. So that means that that angle, this is not... Right, it is not a right angle, so meaning it is not a right triangle. Okay, if we get a true statement, then it is, right? It's correct. Let's look on the back side. Let's look at example 2 now. Right, we have to determine if this, again, I'll put a question mark here. Is this a right triangle? Is that a right angle? It looks like it, but again, we have to prove it. The opposite that supposed right angle is 10. We'll say that that's C. So I'm just going to put on the right side, we'll put 10 squared. I'll put A for 6 or and B for 8. But again, like we said, we can switch that. So let's put 6 squared plus 8 squared. All right, 6 squared is 36. 8 squared, we just did that earlier, is 64. And 10 squared is 100. If you add the left side, right, let's add our ones place. 6 plus 4 is 10. So we could put a 0 here. You'd have to carry the 1. So right? 3 plus 6 or 30 plus 60 is 90 plus that extra 1 or that extra 10, 90 plus 10, right, is 100. So we have a true statement here. When you have that true statement, this tells us that this triangle, right, has a right angle, so it is a right triangle. Just abbreviate there. Okay, so we use the Pythagorean theorem to prove, right, do these angles, is it 90 degrees? Right, so if we're making, manufacturing parts that then need to have a specific angle, that's one way to prove it. We're going to go to this last part where we do have a right triangle, and we're using the Pythagorean theorem. So if a triangle is a right triangle, then we can use this formula. We've been using the converse, which is if that formula is true, then we can determine that what type of triangle that is. But here we're trying to find this missing measurement, and we have some numbers, but we're missing a specific side length. So for this one, we're missing the hypotenuse. So let's go and plug this into the Pythagorean theorem. So a squared plus b squared is equal to c squared. So this is going to be 2 squared plus 5 squared. And this, again, is opposite the right angle. We're going to say that this is equal to c. We can put c squared, or, I'll just keep it as x squared. So for this, right, we have 4 plus 25 equals x squared. We're going to simplify the right side, which is 29. And when you solve this, so what we want to do is we want to get rid of that square. The inverse of squaring a number is taking the square root of that number. So typically I'll always say that squares undo square roots. So what I'll do is I'll cross both of them off. And I'll put equal to. We just have x, we have our radicand. Square root of 29. Now, if you remember simplifying square roots, we have to find what this is in between, right? 29 is in between square root of 25, right? Which two perfect squares? And square root of 36. Right, I'm getting this from our last lesson. Square root of 25 is 5, and square root of 36 is 6. If I put 29 in here, whoops. That's 4 away from 25, and that is, looks like 7 away from here. So it's going to be 5 point something. It's going to be slightly closer to 5. So this is going to be a number that's slightly closer to 5. Let's say 5.3. If you check this using your calculator, you're going to get a number very close if you round it to 5 3/10. Okay, and now the last part here, we're now trying to find one of the legs here. We're going to say that this is C, right, opposite. This is 12 is B, and we'll say A is X. So again, rewriting the formula, last time, we'll put x squared plus 12 squared, and our biggest number, 13 squared. Now, nothing's going to happen with x squared because we don't have a value for it, but we can simplify our numerical terms. So 12 squared is, whoops, this should be plus, 144. 13 squared is 169. And if you remember from solving equations, we do have to isolate our variables. So we're going to get rid of our constant, right? It's adding, so we're going to subtract 144 to both sides. We'll have x squared equal to, subtracting here, right, 9 minus 4 will give us 5. And 16 minus 14 is 2. So in order to get our answer, we're going to take the square root of both sides to get rid of the square. But I also have to do this to the right side. And this is a perfect square root. We know how to simplify this, right? Square root of 25 is 5. So final answer is that this side length right here has to be 5 units. All right, so we're going to further practice Pythagorean theorem, but for right now, let's go and move on to our math here practice. Let me know if you have any questions.